As usual, I expect the session to go in an interactive way, where students can raise their questions and answers by unmuting themselves or using the chat box. Secondly, the contents of the session will be a summary of the lectures that are part of the last week. So this summary, I hope it will be useful for you in solving the or giving answers to the assignment. Further, I'll be taking up some sample problems and I'll be solving the and providing the solutions in the live. Then it's a time for questions. Okay. In the last week, we have been discussing about the protein structural analysis. So, I would like to give a brief intro about why and how it is useful for our bioinformatics analysis. So, computational protein structural analysis is a broad field that involves various techniques and tools for studying structure, function, and dynamics of proteins. Here are some of the features of computational protein structure analysis. First one is structure prediction. One of the primary features of computational protein structure analysis is predicting 3D structure of a protein from its amino acid sequence. This structure prediction involves algorithms and computational methods to predict the most energetically favorable conformation of protein. Next is the structure alignment, which is a process of comparing 3D structures of two or more proteins to identify similarities and differences among them. This structural alignment is useful for understanding evolutionary relationships, identifying functionally important regions, and designing new proteins. Next one is molecular docking. So molecular docking is used to predict the binding mode of a ligand or is used to get the complex structure. The complex involves protein and a ligand or protein and it could be any ligand like small molecule ligand, DNA ligand or the carbohydrates as ligand. So this docking involves generating the different conformation of the ligand and calculates the energy of the interaction as well. Next is molecular dynamic simulations. So they used to study the dynamic behavior of the proteins at atomic level. This molecular dynamic simulations basically works on Newton equations of motion. So this method applies these equations of motion for all the atoms in the proteins. So which allows researchers or the people who are using this to study protein dynamics, conformational changes, and protein ligand interactions. Next one are protein-protein interaction analysis. So used to study the protein-protein interactions and involves the predicting binding sites and affinity of the protein-protein interactions as well as the structural and dynamic changes that occur during the interaction. A last one is the structure-based drug design. So this is comes under the docking or so which helps us to design or confirm whether the new drug that binds to a specific protein target. So this method involves predicting the binding site and affinity of potential drug molecules and designing molecules that optimize the interaction with the target protein. So in the last week session, we have discussed some of the structure-based features. Now I'll continue from that. So the first one today we are going to discuss is about the B factor, which is also known as temperature factor. So this B factor is a measure of atomic displacement or mobility within a protein crystal structure. It provides information about the flexibility of protein structure and is important parameter in understanding the protein dynamics and function. This B factor values are typically reported in Armstrong square and are calculated from atomic mean square displacement, which is derived from the crystallographic data. So here is the example that I am showing how a crystallography or the PDB data of a residue looks like, and here is the B factor column given and the units for this B factor is Armstrong square. Here, higher B factor values indicate higher atomic mobility or displacement, while a lower B factor values indicate lower mobility or displacement. However, the absolute B factor values can vary significantly between crystal structures, making it difficult to compare the flexibility of different proteins or different regions within the same protein. So, therefore, normalized B factors come into the picture. So, these normalized B factors are often used to account for the variations that are generated due to the absolute B factors and allows us to make a more meaningful comparisons. These normalized B factors are also known as relative B factors and are calculated by dividing the B factor value of each atom by the average B factor value of all the atoms in the crystal structure. So this allows for the comparison of relative mobility or flexibility of different regions within the same protein or different proteins. These normalized B factor values are useful in identifying the flexible regions within a protein that may be important for functions such as active sites or binding sites. They can also use to compare the flexibility of different protein structures and to study effect of mutations or ligands on protein flexibility. In summary, B factor and normalized B factor are measures of atomic displacement or mobility within a protein crystal structure, while a B factor provides absolute values of mobility. Normalized B factor allows for one more meaningful comparison of relative flexibility between the region or proteins. Next is we'll start with the center of mass, so which is a point that represents average position of all atoms in the proteins weighted by their masses, like atom masses. It is a useful parameter for studying the overall structure and dynamics of the protein, as well as simulating the movement and interactions of the protein with other molecules. Here I have given a formula. So the formula for computing is here x is represents the Cartesian coordinate x, and the x coordinate for center of mass is given as xcom, which is calculated by summation of product of atomic masses into the Cartesian coordinate divided by the sum of the masses. Similarly, the y-z coordinates of the center of mass can also be calculated. In practice, these position vector or masses of the atoms can be obtained from protein structural file such as PDB. Like in the previous slide, we have discussed the PDB format where we have these Cartesian coordinates and the atom that corresponding atom is present. So this center of mass can provide valuable information about the overall shape and orientation of a protein as well as its movement and interaction with the other molecules. For example, the distance between center of mass of two proteins can be used to estimate the strength of their interaction or likelihood of their binding. The center of mass can also be used to define the reference frame of a protein for molecular dynamic simulation or other computational analysis. By setting the center of mass as origin and aligning the principal axis of the protein with the Cartesian axis, the Cartesian axes are nothing but x, y, z axes, the protein can be simulated in a more natural and physically meaningful way. In summary, the center of mass of a protein is a point that represents the average position of all atoms in a protein weighted by their masses. It is calculated using the formula given here. Here m corresponds to the atomic mass, and finally to conclude, center of mass can provide valuable information for studying the structure, dynamics and interactions of proteins. Next thing is radius of gyration, which is a measure of compactness or size of a protein and is commonly used in the analysis of protein structure and folding. Radius of gyration is calculated as root mean square distance of all the atoms in the protein from the center of mass of the protein. So here the formula is given. The distance of each atom from center of mass can be calculated as Ri, which is uh, R could be xyz and minus center of mass. So the radius of gyration needs this value for calculating. So radius of gyration is a useful parameter for characterizing the size and shape of a protein as well as for studying its folding and stability. A larger radius of gyration indicates more extended or flexible structure, while a smaller radius of gyration indicates a more compact or rigid structure. In addition, the radius of gyration can be used to compare the size and shape of different proteins or different conformations of the same protein. It can also be used to analyze the effects of mutations or ligand binding on protein structure and dynamics. In summary, the radius of gyration of a protein is a measure of its size and compactness, which is calculated as root mean square distance of all atoms from the center of mass of the protein. Okay, next is the protein residue uh, interactions. So these are also can be referred as non-covalent interactions between amino acid residues in a protein structure, so which are essential for stabilizing the protein structure and enabling its function. So these residue interactions or covalent interactions can be classified into several types based on the nature of the interaction and distance between the interacting atoms. So first, let me start with the disulfide bonds. So disulfide bonds are type of covalent bonds that form between the sulfur atoms of two cysteine residues, and they need an oxidizing environment for forming the disulfide bond. So the typical cutoff distance for disulfide bond is around 2 to 2.5 angstroms. Next is the ionic interactions, which are formed between the positively charged and negatively charged amino acids. Typically, the cutoff for them is around 6 angstrom. Next are the hydrophobic interactions, which involves the interactions between the hydrophobic residues. So, and this is calculated if the hydrophobic residues fall within the cutoff of 5 angstrom distance. Here, the distance uh, formula is given. This is a Euclidean distance formula, which is a square root of sum of the squares, different squares of the Cartesian coordinates, which is used to calculate the interactions. Next are aromatic interactions. These are also called as the cutoff for ionic interactions is around 6 Armstrongs. Generally, it varies from 5 to 6, in between 5 to 6. Based on the class of proteins, like when we take globular proteins, they used to be on cutoff. But this is the average overall, like this is the consolidated average cutoff. Okay, moving forward, aromatic interactions. These are also called as pi-pi interactions, which occur between two aromatic rings, such as those of phenylalanine or tyrosine, which are stacked on top of each other. The typical cutoff for pi-pi interactions is around 4.5 to 7 Armstrong. Next is the aromatic sulfur interaction. Similarly, where this is between the aromatic rings of phenylalanine and tyrosine with sulfur containing amino acids. So they have the average cutoff for taking into consideration of aromatic sulfur interactions is 5.3 angstroms. Next are cation pi. So these interactions occur between an aromatic ring and a positively charged amino acids such as lysine and arginine. So here the cutoff, the maximum range cutoff for this is 10 angstroms. So coming to these cutoff distances, how they came, so they are typically based on empirical observations and may vary depending on specific context and purpose of the analysis. However, these values provide here a general guideline for identifying and analyzing the protein residue-residue interactions in protein structure. The identification and analysis of protein residue-residue interactions can provide insight into the stability, so which we will be discussing about stability in the later half of this session, function and evolution of proteins, and can also guide the design of new proteins with desired properties. Okay, yeah. So far I have done with these protein structural features. Any doubts before moving forward, you can ask me through chat box or unmute yourself. Next, I will be discussing about superimposition, followed by the how we sequence to structure building. Then, in the last part of the session, we will be discussing about the protein stability. Okay. If no questions, okay, let me move forward. Okay, next, we are discussing about the structure superimposition. So, which is a process of aligning two or more protein structures to compare their similarities and differences. There are several algorithms available for performing protein structure superimposition, each with its own strength and limitations. So here I'll be discussing some commonly used algorithms for protein structure superimposition. First one is least square fitting method. So this algorithm involves aligning two protein structures based on the superimposition of their C alpha atoms, like C alpha, like a carbon atoms in the backbone. So this least square fitting algorithm minimizes the root mean square deviation between the two structures by minimizing the sum of the square distances between the corresponding C alpha atoms. This algorithm is simple and fast but may not capture the full complexity of the structural differences between the two proteins. As I mentioned before, so these algorithms have its own strength and limitations. Next is the dynamic programming algorithm, so which uses a dynamic programming matrix to iteratively align two protein structures based on their overall structural similarity. This algorithm can handle more complex structural differences between proteins than the least square fitting algorithm, but may be slower and computationally intensive. Next is the iterative algorithms, such as iterative magic fit IMF or iterative structure fit ISR, which uses an iterative process to refine the superimposition of two protein structures based on their local structural similarity. These algorithms can handle more complex, like iterative algorithms can handle more complex structural differences between the proteins than the least square fit algorithm and can provide accurate superimposition result. Next is the multiscale methods such as multiscale orientational matching MOM algorithm or multiscale SVD, MSSVD algorithm, which uses a hierarchical approach to align two protein structures based on their structural similarity at different levels of detail. So these multi-scale methods can handle large structural differences between proteins and can provide more accurate superimposition results than other algorithms. Next is the geometric hashing. Geometric hashing algorithm uses a geometric representation of protein structures to identify the similar structural motifs between two proteins and to align them based on their shared motifs. So these algorithms can handle large structural differences between the proteins and can provide comparatively accurate superimposition results. So each of these algorithms has own advantages and disadvantages and is best suited for different types of protein structure superimposition task. Here, the choice of algorithm depends on specific requirements and constraints of the analysis. So here I'll be discussing one method in detail that has been discussed in the NPTEL video as well, that is DALI method, so which stands for distance matrix alignment method. So this is based on the idea of comparing protein structures by aligning their secondary structure elements and calculating the similarity between the structures based on their overall topology. So can anyone let me know, here is a question, let me know what are the two main secondary structure elements in proteins? I am repeating the question. Can anyone let me know what are the two main secondary structure elements in protein structures? I hope I am audible. Yes. Yeah. Thanks for the answer. And yeah, alpha and beta. So here DLI method is based on the idea of Thank you everyone for the answers. Comparing protein structures by aligning their secondary structure elements and calculate the similarity between the structures based on their overall topology. So this method first calculates the distance matrix between all pairs of C alpha atoms in the protein structures. It then identifies the secondary structure elements in each structure and aligns them based on the spatial alignment. The alignment is optimized by minimizing the RMSD between the aligned secondary structure elements, and the similarity score is calculated based on the alignment and distance matrix. So this similarity score is based on number of aligned residues, RMSD between the aligned residues, and the penalty term for gaps and insertions. The DLI method assigns a Z score to each pairwise comparison, indicating the significance of the structural similarity based on the distribution of scores obtained from a database of known protein structures. So this method has been integrated into several software packages, including DLA server or DALI-Lite program. Okay, now we'll be moving into the protein 3D structure prediction. Can anyone mention why we have to predict the structure? Why experimentally we are not getting the structure? Why we have to search for a computational alternative? Could be any reason. I'm repeating the question. Why we have to look for computational alternatives for experimental structures, or why we are not using experiments to get the structure? Yes, as you have mentioned, it takes more time and experimentally costly. Yes, these are correct. So here I'll be discussing about the computational methods that aim to predict the 3D conformation of a protein from its amino acid sequence. So first I'll start with the homology modeling, which is also known as comparative modeling. So this homology modeling involves the prediction of 3D structures based on its homology to a known protein structure. So this method relies on the assumption that protein structures are more conserved than their sequences, and therefore two proteins with similar sequences are likely to have similar structure. So the homology modeling method requires a template structure with high sequence similarity to the target protein and can generate models when the template is of high quality. So here we can get template by using the BLAST analysis. So in the BLAST, we can use BLAST P version of the BLAST, which is protein BLAST, where we can input our unknown structure amino acid sequence into the BLAST and then perform the BLAST using the target database as PDB. Then it gives us the possible or aligned hits from PDB to our input sequences, where this thing, aligned or template can be used for homology modeling. Next is the ab initio methods, which are also called as de novo methods, which predict the protein structure without using template structure. So these methods use a physics-based approach to predict the conformation of a protein by optimizing its energy landscape. So the method is computationally intensive and requires a large amount of computing resource, but it can be applied to proteins with no known homology to any structure. Ab initio methods can generate a model with low accuracy, but their accuracy can be improved by combining them with experimental data. Next is threading. So this is a hybrid method that combines both homology modeling and ab initio method. So where the threading algorithm search a library of protein structures for the best match to the target protein sequence. This threading algorithm generates a model by aligning the template structures to the target sequence and refine it using ab initio approach, and can generate accurate models when suitable template structure is available in the library. Next is hybrid methods. Threading is also one of the hybrid method only. Later followed by the nowadays very famous machine learning methods, which uses deep learning and neural networking to predict the protein structures. So this machine learning method can generate the accurate models with high speed, but they have also have this limitation that they require large amounts of high quality training data to build on, because machine learning methods initially train themselves on the data and then gives us predictions. And here also each of these methods has its own advantage and limitations and are best suited for different types of protein and structural feature analysis. And finally, the choice of the method depends on the specific structure requirements and constraints of the analysis. So here I'll be further discussing homology modeling. So this method relies on the assumption that protein structures are more conserved than their sequences, and therefore two proteins with similar sequences are likely to have similar structures. Homology modeling can be a powerful tool for studying the protein structure, function, designing drugs, and predicting the effect of mutations. So we'll start with the steps involved in the homology modeling. First is the template selection, where the job is to identify a suitable template protein structure that has similarity to the sequence. So the template structure can be obtained from protein structure database such as PDB. Next is the sequence alignment. Where that is the next step is sequence alignment, that is to align the target protein sequence with the template protein sequence using sequence alignment tools. The alignment should be optimized to maximize the sequence similarity between the two proteins. Next is the model building. Once sequence alignment is completed, the model can be built by transferring the coordinates of the atoms from the template structure to the target sequence. So this can be done by using software such as Modeler or Swiss Modeler. Next is the model evaluation. The homology model should be evaluated to ensure that it is of high quality and accuracy. This can be done using tools such as ProCheck or MolProbe, which evaluates the quality of the model based on various criteria such as bond lengths, angles, torsion angles, and packing density. A final one is the model refinement, where the homology model can be further refined using energy minimization or molecular dynamic simulations to optimize the structure or to remove any steric clashes or structural errors. Okay, next on, we will be moving to the ab initio proteins prediction, ab initio methods, which aim to predict the protein structure solely based on its amino acid sequence without relying any prior knowledge of its structure or homologous sequence of structures. So these methods are particularly useful for predicting structure of a proteins that have no homologous structures in the PDB data bank. Like we all know, PDB is the only available or large resource that has the protein structures. So the basic idea behind the ab initio structure prediction is to generate the large number of 3D conformation of a proteins and then to search for the conformation with lowest energy, which is assumed to be the native structure. So the energy of each conformation is calculated using a physics-based energy function that takes into account the electrostatic, van der Waals, and other physical interactions between the atoms. So the steps involved in the ab initio prediction process are fragment assembly, where target is to generate the large number of short protein fragments, typically 3 to 9 residues in length, so which represent the possible building blocks of the protein structure. The next step is to assemble these fragments into a 3D conformation of the protein. This is done by performing a Monte Carlo search through the conformational space, which involves randomly selecting the rotating fragments and evaluating the energy of the resulting conformation. This process is repeated thousands or millions of times to generate a large number of possible conformations. Once a large number of conformations have been generated, their energies are evaluated using a physics-based function that takes into account the interactions between the atoms. The lowest energy conformation is assumed to be the native structure. Final step is to refine the predictor structure using energy minimization or molecular dynamic simulation, which helps to optimize the structure and remove any steric clashes or structural errors. So the problem or limitation with the ab initio structure prediction methods is they can be computationally intensive and require powerful computational resources. However, they can be very useful for predicting the structure of the protein that are difficult to study using experimental techniques such as for membrane proteins or protein-protein complexes. So some examples of ab initio methods are Rosetta, which is a widely used ab initio method that uses a fragment-based approach and a physics-based energy function to predict the 3D structure of a protein. Next is ITASR, which is an hybrid protein that combines this hybrid method that combines the ab initio methods with homology modeling to predict the 3D structure. Next is Quark, which is a combinations of fragment-based assembly and replica exchange Monte Carlo simulations to predict the 3D structure. Ab initio protein structure prediction methods have made significant progress in recent years and have been successful in predicting the structures of several small proteins with high accuracy. However, predicting the structure of larger or more complex protein remains a major challenge for ab initio methods, and further developments in algorithms or computational techniques needed to improve their accuracy and reliability in case of predicting the structure of larger and more complex proteins. So here I'll be discussing about today's most known method, that is AlphaFold. So AlphaFold is an artificial intelligence program developed by DeepMind that predicts the three-dimensional structure of a protein from its amino acid sequence. The program uses a combination of deep neural networks and genetic algorithms to model the protein folding. So this protein folding is critical for understanding the protein function and designing new drugs. So here I'll be discussing the steps involved in the AlphaFold. The first step is data collection. So that involves including collecting data on the protein of interest, including its amino acid sequence or any related structural information available from experimental studies. The second step is to perform a multiple sequence alignment of the amino acid sequence with other related sequences from a variety of algorithms. This step helps to identify any conserved residues or patterns in the sequence that may be important for structure prediction. The third step is to extract features from aligned sequence data, including information on amino acid sequence, evolutionary conservation, and other physicochemical properties. These features are used to train the deep neural network. The fourth step involves the training a deep neural network to predict the 3D structure of the protein. This is done using a combination of supervised and unsupervised learning techniques, where the network is trained to predict the 3D structure from experimental data and also from simulated data by generating a genetic algorithm. The fifth step is to use the trained neural network to predict the 3D structure of the protein. This is done by feeding the amino acid sequence and extracted features into the neural network, which outputs a predicted 3D structure. Next is the model refinement. The final step involves the refining the predicted structure using a variety of techniques, including energy minimization, loop modeling, sidechain optimization. So this step is important to ensure that predicted structure is stable and biologically relevant. AlphaFold represents a significant advance in protein structure prediction and has potential to greatly accelerate the development of new drugs. And so when we compare AlphaFold to homology modeling, so homology modeling is only the structure based. Here, AlphaFold takes in the information, uses a Evo transformer, which is a part of a deep neural network, to combine or to interact between the information available from sequence alignment as well as the template structures. So this made it this crosstalk between the two feature paths made AlphaFold a good alternative to homology modeling. Okay, here on I'll be moving to protein stability. So protein stability refers to the ability of a protein to maintain its native conformation or structure under a range of environmental conditions such as changes in temperature, pH, ionic strength, and pressure. The stability of a protein is important for its function as well as for design of protein-based drugs or therapies. Protein stability is determined by complex interplay of various factors including protein structure. So the folding of a protein into its native conformation is a result of delicate balance between the attractive and repulsive forces among the amino acid residues. The structure of a protein is stabilized by various interactions such as hydrogen bonds, disulfide bonds, van der Waals forces, and hydrophobic interactions. Further, the solvent environment, including pH, ionic strength, and temperature, can affect the stability of a protein by altering the balance of electrostatic and hydrophobic interactions among the amino acid residues. Changes in pH or ionic strength can disrupt the hydrogen bonding or electrostatic interactions, leading to protein denaturation or unfolding. Next, chemical modifications such as phosphorylation, glycosylation can alter the stability of a protein by changing its structure or interactions with the other molecules. For example, phosphorylation can change the charge or conformation of a protein, while glycosylation can protect the protein from denaturation or proteolysis. Chaperones and other proteins can assist in the folding and stabilization of proteins by providing a protected environment and promoting corrected folding pathways or preventing aggregation or misfolding. Finally, ligand and substrates can stabilize or destabilize proteins by altering their conformation or interactions. For example, the binding of a substrate can stabilize the active conformation of enzyme, while the binding of an inhibitor can destabilize the. See, overall, the stability of a protein is a complex and a dynamic property that is critical for its function and biological activity. Understanding the factors that contribute to the protein stability can help in the design of more stable proteins for therapeutic applications. So in this concept, I'll be giving Gibbs energy because in most of the recent day studies, Gibbs free energy of unfolding, that is observed, calculated using the unfolding studies, is considered as a measure of stability of a protein and describes the change in free energy when a protein unfolds from its native conformation to its denatured state. So can anyone mention what are the agents that are used for protein denaturation? I'm repeating the question. Can anyone mention what are the agents? So in chemical denaturation studies or thermal denaturation studies, what are the agents that are used to observe the unfolding pattern of a protein or to study the unfolding? Okay, actually temperature based unfolding where we increase the temperature to unfold the protein, or urea based where urea is used as a denaturant. Okay, so experimentally how to measure the delta G. So differential scanning calorimetry measures the heat absorbed or released by a protein as it undergoes the thermal denaturation. By analyzing the temperature dependence of heat capacity, delta G of unfolding can be calculated. Next is this circular dichroism, which measures the changes in secondary structure of a protein as it undergoes denaturation. By analyzing the temperature dependence of CD signal, delta G of unfolding can be calculated. Next is fluorescence spectroscopy, measures the changes in the fluorescence intensity or emission wavelength of a protein as it undergoes denaturation. By analyzing the temperature dependence of fluorescence signal, delta G of unfolding can be calculated. Next is chemical denaturation, which involves the use of denaturation such as urea, guanidinium chloride to induce protein folding. By measuring the change in protein stability as a function of denaturant concentration, delta G unfolding can be calculated. Next is the mechanical unfolding. So mechanical unfolding involves the use of atomic force microscopy or optical tweezers to stretch a protein until it unfolds. So by applying the force extension curve, delta G of unfolding can be calculated. Overall, the experimental measure of delta G of protein unfolding is an important tool for understanding the protein stability and for the design of protein-based drugs and therapies. By combining the experimental measures with computational modeling, it is possible to gain a deeper understanding of the factors that contribute to the protein stability and to design the more stable proteins. So here I am done with my summary. So before moving on to the assignment, I would like to take any questions if at all. Yes, please you can unmute and ask. What do you mean by three structures here? Do you mean the structures which are generated? Yeah, primary is same. Primary is just a chain of the amino acids. Next, secondary structures and 3D structures are generally secondary structures. We are already having a lot of knowledge on secondary structures, so mostly they won't be different. We have a high accuracy in predicting secondary structures. When coming to the 3D structures, we encounter the flexible loops and turns. That makes us the complexity in placing these secondary structures towards them. So that is why these different computational tools comes into play with different techniques to build the overall the principle of secondary structures or the bonding pattern in secondary structures or the uh, in 3D structures remain same either experimentally or when we take it computationally. Okay, okay. Moving forward, here is the first question. The question is normalized B factor of a residue depends on normalized B factor of a residue depends on a B factor of a specific residue, mean B factor, or deviation of B factors, or all of the above. Yeah, here we are moving on to the assignment. You can answer these questions using the chat box. Okay, I started receiving the answers. I'll wait for a minute for others to read and answer. Yeah, we have discussed about the B factor before. So how a normalized B factor has been calculated? Yes, okay. Yeah, here the answer is D. The calculation or the normalized B factor of a residue depends on the B factor of specific residue, mean B factor, and deviation of B factors. Here, how it is calculated means B factor of a residue minus average B factor of all residues divided by standard deviation of B factors of all residues. So this is similar to the Z score that we calculate. Value minus mean divided by standard deviation. So this B factor is a measure of average thermal motion of atoms in that residue and is typically reported in Armstrong square. Okay, let us move on to the next question. So given XYZ coordinates of an alanine residue, can you calculate the center of mass of this residue? Okay, I'll provide you with a formula as well. The formula is given here, where in the formula M corresponds to the atomic mass, X corresponds to the X Cartesian coordinate. Similarly, as here the formula shows for X, for Y and Z also we can calculate. So here I know this is some requires some calculations. I'll wait for that until you finish the calculation. The answers. Okay. Uh, we'll move on to the solution. I'll show how to solve. Give me a minute. I'll reshare my screen again. Okay, here when we consider the given atoms are C and O. So what will be there? First, let's know what is their atomic weights. So the atomic weight of carbon will be 12, nitrogen will be 14, and oxygen will be 16. So given their atomic weight, let's try to calculate for x coordinate of center of mass. Just give me a second. So we have this first thing is nitrogen atom, and its x coordinate is 6.3, plus next we have C alpha, so that is carbon atom, so 12 into, and its x coordinate is 6.1, plus next we have again a carbon, so 12 into, its coordinate is 7.4, plus next we have oxygen, where 16 into 7.4, plus finally we have again carbon, so 12 into 5.9 divided by sum of all the atoms that we consider, that is 14, 12, 12, 16 plus 12. So average value will be 439.4, I think so, divided by 66. So which gives you around 6.7 as the answer. So any doubts and how I got this? Similarly, you can apply the same to y coordinates and z coordinates, and you can get those. Yeah, your answer is correct. Someone has mentioned the answer. Here the answer is E. Okay, moving on to the third question. So in homology modeling, if 100 residues are aligned with, yeah, three is says three times. Yeah, we can do that because we have three like we have a carbon in the name of C alpha, like Ca, C, and Cb. So that's why three times carbon has been considered. Okay, next we'll move on to the homology modeling question. So in homology modeling, if 100 residues are aligned with 30% sequence identity, in which zone does it fall? Okay, I have answers here. Moving on to the solution, the answer is twilight zone. So this twilight zone refers to a situation where sequence identity between the target protein and template protein is less than 30%, making it difficult to accurately model the structure. So at this level of sequence identity, the structure of the protein is likely to differ significantly from that of template protein. So this can make it challenging to accurately predict the folding and packing of the target protein. Okay, let's go on to the next question. So which of the following, so we are doing the fourth question now. Which of the following structure prediction method does not rely on a template structure? Yeah. So twilight zone is a situation where sequence identity of target protein and the template is less than 30%. So twilight zone refers to a situation where our target protein sequence and template protein, when we align them, we have less than 30%. Think we have 100 residue length, out of which only 30 residues are identical to it, or less than 30 are identical. This doesn't fall under a twilight zone. Yeah, so equal to 30, like one residue, because we are taking in a residues of normally 300 to 400 length proteins. So 30% or less than 30% makes equal sense. It's just a cutoff that is given. Even 31%, 32% could also be sometimes gives us the wrong results. Or the concept here is how when we are using homology modeling, as the template identity decreases, our structure accuracy or the actual structure started will deviate from the template structure. So that is what this concept is. Yeah, here coming to this fourth. Okay, and the answer is Ab initio modeling. So where we discussed it, they have to predict the protein structure solely based on amino acid sequence without using any information from experimentally determined structures or homology modeling. Next is, which of the following is dominant in unfolded state of a protein? So this is the question that is related to the folding and unfolding. So we have discussed the factors that help in folding of a protein. So here the question is about the dominant factors in unfolded state of a protein. Okay, some answers. Yeah, here when we see the options, um, first three options corresponding to the covalent interactions that we see, non-covalent interactions that we see. Next is the entropy. So entropy refers to the randomness or disorder in the system. So when we consider a folded protein, so the folded protein tend to have its maintain its 3D conformation using these interactions. That these interactions uh, held the protein in this structure. So where the randomness of the protein is decreased. Where coming to entropy, the entropy of a protein in folded state is very less. In unfolded state, when you say linear chain of protein, it can be folded into infinity conformations. So that means in an unfolded state, the dominant is entropy. So which is random. So when you have a linear chain or a linear thread, you can make it n number of shapes. So that is what the concept here. The answer is entropy. In an unfolded state, entropy is the dominant force. And there is an concept called entropy loss or entropy loss by the protein and entropy gain by the surrounding water during folding of a protein, which gives us a very good idea about what entropy and how the Gibbs free energy is calculated based on this entropy. Okay, moving forward. So, in general, the free energy change between the folded and unfolded state of a protein is in the range of. Okay, I think this is pretty easy question. Can anyone tell why it is in that range only? Like why the range is small, not so high? Yeah, the structures are marginally stable because the stability is also known as difference of free energy between folded and unfolded stage is also called as stability. This stability has takes lower values because it's a balance of attractive and repulsive forces. That's why these values are very in marginal range, low range. So here the answer is 5 to 25. So here the why not option here, since I told it could be less or more, why not option here? So 0 to 5 is such a way that there is no difference itself. There are very less low values. And this 5 to 25 is the stability range values for globular proteins. Coming to the membrane proteins, the stability range decreases further. Next is the Which of the following interaction is modeled using Lennard-Jones potential during MD simulation? I know MD simulation is not part of this, but here is a basic question. Okay, here the answer is the LJ potential is used to calculate the van der Waal interactions. Electrostatic interactions are calculated using the formula 1 by 4 pi epsilon naught q1 by q2 by r square. Or, yeah. So Lennard-Jones potential takes into the concept of 1 by r to the power of 6 minus 1 by r to the power of 12 and depth, the graph depth and all to calculate the van der Waal interactions, not electrostatic interaction. Next is which of the following method is used for measuring folding free energies? So given some experimental techniques, which of the following are used to measure folding free energy? Yeah, folding free energy means nothing but Gibbs free energy delta G. Okay. Here the answer is all. Circular dichroism, differential scanning calorimetry and fluorescence spectroscopy were used for predicting the folding free energy or unfolding free energy. Just the folding free energy and unfolding free energy will have only the sign difference unless transition states are not considered, are considered. Sorry. Okay, we are left with a couple more questions only. Rosetta is a web server that predicts a protein three-dimensional conformation using the ab initio method. True or false? I hope we have discussed about Rosetta. Yes, it is true. Next is moving on to the 10th question. There are large number of protein folds available compared to the millions of protein sequences. True or false? Yes, the answer here will be false because there are less protein folds available than compared to the million. That is why the concept of computational protein structure prediction comes into play. So we know very less number of sequences, and there are protein sequences whose structure is not yet known. Moving on to the other question. Which of the following is used for validating the model protein structures? Okay. So here the answer is Procheck. Procheck and Nullprobe are the tool that used to validate the models. Swiss model uh, is used for generating the models, and this Procheck and Nullprobe are part of Swiss model as well. I think this is the last question for the day. So when you have a protein sequence and you want to quickly predict its structure, after performing the blast searches, you identify the most closely related proteins with a known structure having 50% amino acid identity to your protein with a non-significant E value, that expect value. So which of these options is best? And here we are done with the questions, and any doubts you can ask me. If no doubts, you're free to leave. Thanks for attending the session. Okay, B, NMR. Yeah, so when we having a very less identity cutoff of 15%, the homology modeling fails to predict. In generally, homology modeling is considered good. Predictions made by the homology modeling are considered good only if the identity cutoff identity is more. And X-ray and NMR are experimental techniques which they have their limitations as well. So submitting the sequence to predict the ab initio method is the best option when we don't have the sequence that good sequence identity or similarity. Yeah, so this is for today. Uh, I would like to take questions if there are any questions. If no questions, you're free to free. Thank you for attending the class. I'll wait here for a couple of minutes to take questions.